All right, so last time we talked about reaction diagram, coordinates. We had the Arrhenius equation. We had this guy, right? That one, where I have A plus B goes to P plus Q. We have delta G double dagger and then the delta G of reaction. Good? Okay. So, reactions more often occur in two steps rather than what we looked at last time. Last time it was A plus B goes to P plus Q. It's more typical to have a reaction that goes through an intermediate stage. So I'm showing the reaction of A goes to I, goes to P. Where I stands for intermediate. Which means there's going to be two transition steps or states, whatever you want to call them, and then there has to be two activation barriers because I'm going to pit stop at I and then head on to P. So let me ask some questions to go along with this thought. Come over here. All right, so the first question is, what if the activation energy of the first step, and what's the letter combination I would use to describe the activation energy? I'll give you a hint, start with the delta. Double dagger, that's this guy. So what if the delta G double dagger of the first step is greater than that of the second step? Which one of the two steps is slower? First one. So instead of me writing out the exact reverse of the question above, you can rewrite it. But what if the activation energy of the second step is greater than that of the first step? Which of the two steps will now be the slower? Second step, right? Then what do we call that step that is the slow step of all the steps? Rate determining step. Oh, I have a little bit of space down here. So the slower step is the rate determining step, which is directly related to the delta G double dagger. So in the first thing, right, first step must be slower. So if that's slower, then that is the rate determining step. If the second one is slower, then the second one is the rate determining step. So let's look at my reaction coordinate diagram that's on this page. And look at which one of these two is the slower step. All right, so I got my reaction coordinate across the bottom. I got my free energy on the y-axis. Is overall this reaction spontaneous or non-spontaneous? Spontaneous. How do you know it's spontaneous? Negative delta G, and we measure delta G from here to there. I'll explain why I have two sets of lines here in a second. All right, so I have two different delta G double dagger steps. I have one from here to here. Oh, that one should be there, there. All right, so I'm at A, how high the activation barrier is compared to where I start. And the second one for I, how high this one is compared to where it starts. Now, eyeballing, which one of those delta G double daggers seems larger? I think the second one's slightly bigger. This one right here. I think in terms of height, if that's one knuckle, that's like a knuckle and a half. I don't know. I'm going to guess this one's slightly bigger. So if the second one's slightly bigger, which part of this is the rate determining step? Which would be what in terms of arrow to arrow? I to P. I to P is our rate determining step. Good there? Thinking through that thought process seems all right. Excellent, like stairs. Good. All right, how are we doing at writing all this down?
One question.
Oh, yeah.
For the second step, when you drew the delta G double dagger, is it going to the top of that curve there?
Yeah, it should be this point to that point. Okay, then let's talk about how do enzymes affect reaction coordinates. Enzymes, specifically catalysts. So catalysts, which is what enzymes are, reduce the delta G double dagger. Enzymes or catalysts provide a reaction pathway with a transition state that has a lower free energy than that of the uncatalyzed reaction. Okay, so we're going to spend a lot of time looking at this picture. Okay, here is my reaction, right? I have A plus B going to P plus Q, like we had a little while ago. Here's my uncatalyzed reaction. This one, right, that's uncatalyzed. Yeah, if you have color coding, this would be a good page to color code on also. Okay, so the top one, my blue, is the uncatalyzed reaction. So that's just the reaction all by itself, just happening. The lower one is going to be my red one, and that's going to be my catalyzed reaction. So let's ask some questions about this. Did adding a catalyst change my delta G? how do I measure just flat out delta G? Products to reactants, right? Did it make any difference if I went through the catalyzed version of this or the uncatalyzed? No. It's the exact same number. Did it change the sign of delta G? No. So it didn't change the numerical amount, it didn't change the sign of delta G. Delta G stayed the same. Let's look at my delta G double dagger. Where do I measure delta G double dagger from to? Okay. So I'm going to have two different delta G double daggers then. I have one for my catalyzed reaction, which is from reactants to the top of the catalyzed peak. Then I have a different delta G from reactants to uncatalyzed. Which of these two delta G double daggers is larger? Catalyzed or uncatalyzed? Uncatalyzed. Do it actually in blue.
Absolutely.
Yeah.
Because catalyst lowers activation energy,
Mm-hmm. Mm-hmm. Yep.
so that's for every coordinate.
For every coordinate, correct. Mm-hmm. So that should be blue. Blue is greater than red. Okay. Yeah.
Could you dash the paper over just a little bit?
Which way?
So we can, so I can see the, yeah.
Okay.
Yeah. Thank you.
By how much did delta G double dagger get lowered? Reading off of the graph. I'm just going to go with the letters. By that much. Delta delta G double dagger. So the change in the change of free energy.
Is that line just going between?
Yep.
catalyzed and uncatalyzed?
Yep, it's going from the top of the bottom of that one to the top of this one. So it's just that space, just right there. Yep, that's delta delta G. So the difference between the two peaks. So a catalyst lowers the free energy barrier or the activation energy. Did it lower it? Now, there's an equilibrium, right? So if I'm going in the forward direction, we said it was spontaneous. What about going in the reverse direction, spontaneous or non-spontaneous? Non-spontaneous. Did the catalyst lower the activation energy the same amount if I went forwards or backwards? It did, right? So if I go this way, it's that much delta, like the delta G is a constant, regardless if I'm going forwards or backwards. So delta G is going to be a constant regardless if I'm going forward in the reaction, so the spontaneous direction, or if I'm going the backwards direction, the non-spontaneous direction. So catalyst just overall lowers the activation barrier. Let's see, where can I write this? Hang on. There we go. So based on question number 1 that we asked, in this particular case, the catalyst didn't change our delta G. Enzymes or catalysts can never change the delta G. They don't make the reaction more spontaneous or less spontaneous. They just lower the activation barrier. It's the only thing enzymes can do, lower that height of energy. Did my catalyst make this reaction any faster? Trick question, you have no idea. You have no idea. What is the area that we study to talk about rates? Kinetics. This is not a discussion of kinetics. It is a discussion of thermodynamics. So you cannot answer that question. All you know is it is now easier to get from products to reactants, but you still don't know on what time frame we're doing this. Excellent trick question. That may come up on a test. I would put a star by that.
Do some enzymes though?
Some can. Mm-hmm. Yep. So
But you can't just tell.
you can't just tell by looking at this particular diagram.
But doesn't delta G relate to the K and that?
It does relate to it, but they're not directly proportional. That's why there was that squiggly.
Yeah.
So just because my delta, and I mean they're related to delta G and delta G double dagger, but they're not directly related.
You just can't.
Right, you cannot make a straight one-to-one thing. How do we feel about that? Pretty solid? Yeah. Enzymes lower the delta G double dagger, doesn't affect delta G regular. Doesn't necessarily make it any faster, just lowers that barrier. In that case, let's warm up some more of your color coding and we'll start moving into organic mechanisms of enzymes. Okay. So, cofactors and coenzymes. So in an enzyme, functional groups in the active site, which is where the reaction takes place, can perform the same catalytic, that should be functions, not factions. Perform the same catalytic functions as in chemical reactions. And we can do the following three in general. So enzymes can do acid-base, they can do transient covalent bonds, and they can do charge-charge. So we'll look at all three of those. The things functional groups cannot do, they cannot do redox reactions or group transfer reactions. And we'll look at the different reasons for all of that. So you cannot do a redox reaction or a group transfer reaction. You need a cofactor to do that. So let's talk about what cofactors are and how you use them and why you would need them. What does redox stand for? Reduction oxidation reactions. So cofactors are needed for anything that involves a reduction or an oxidation. Cofactors used in redox reactions are going to be typically metals. Why are metals awesome for redox reactions? Look at my periodic table. Right, they have lots of different oxidation states. They could be in 2s and 3s and 4s and 1s, and they can change oxidation states fairly easily. What is one metal that you know off the top of your head definitely can do a reduction oxidation? Iron. Iron's a good choice. Besides the fact that it's my favorite metal. Just is, like everyone has a favorite. Mine's iron. Those are going to be our top 3 cofactors that are metals: iron, copper, and zinc. I'm going to take a little tangent here because metals are interesting and metal poisoning is fascinating, and it applies to cofactors. So the thing about a cofactor is that it's kind of like the heme group, right, where it's not bound to the enzyme. It's loosely held in the center of an active site. Same thing with these metals. They're not covalently bound to the enzyme, so they can be replaced. So especially in the case of zinc, so go into our periodic table. Zinc, element number 30. So I guess as you're looking at the periodic table, right, element number 30, zinc. Zinc can be replaced by cadmium and mercury because they're all in the same column. They're all going to have similar properties. Size is obviously going to be a bit of an issue, but zinc does a great job of being very helpful in your body. Cadmium, mercury, toxic, super toxic. And so when you're exposed to cadmium or mercury, it's going to replace the zinc in those enzymes and cells and ends up with super toxic effects. So, for instance, let's talk about cadmium for just a minute. There's my tangent for the day. I don't know how many people have bought Hannah Montana jewelry in the past 5 or 6 years. But you may remember the scandal that it was being produced in China, and it had super ridiculous amounts of cadmium in it, and it was transferring through the kid's skin into their body. Same thing, I guess McDonald's had some Shrek cups a few years ago that the paint on it had cadmium in it. Because cadmium's a great colorant. Like, it's a paint pigment often, but it can rub off and you can't ingest it. So that's why you're supposed to be careful with products made from China, because they don't have the same safety regulations that we have here about cadmium and lead levels in their toys. So cadmium, so cadmium poisoning. Typically, you end up with cases such as the flu, so you just end up with like not feeling great, you got chills, aches. Depending on how you ingested it, you may have like some lung irritation if you breathed it in. But chronic exposure leads to bone softening, because it's replacing some of the critical minerals in your bones. Kidney failure, because again, the metal is replacing some of the critical metals used to kind of clean out your uric acid cycle. That's not how you spell arthritis. How you spell arthritis? R. I mean, that's closer. So after your kidney fails, the uric acid isn't being expelled from your body anymore, so it turns out it starts forming in your joints. That's incredibly painful to have crystals forming in your soft tissue in that way. And so in rare cases, you can also lose your sense of smell. So that's just a kind of weird side effect. They lose their ability to smell anything.
What happened to the kids?
I think what they saw is they started to see some of the kidney failure, and they went back to see what the issue was. And if you catch it soon enough, it's reversible. But when it gets to the point that it's chronic, then it's dialysis. I think in the case of McDonald's cups, they caught them soon enough that people in general were safe on that. I have it down here. Yeah, the Walmart Miley Cyrus jewelry ended up being on the shelves for much, much, much too long. And so I think they're probably still figuring out how long you wore it. Probably depends on how much of these effects you're going to see. So always check your labels, see where it comes from. Most importantly, don't eat paint in general. That's a pretty good life rule, especially in this case. Don't lick the outside of McDonald's cups, because that's where the issue was. So.
What's the one similar to mercury at the moment?
You don't like.
Mercury poisoning is my next one. So besides replacing zinc in some of the active sites, it also has the ability to replace selenium, which is also found in some of your enzymes is needed. Mercury poisoning has the largest effect in that it shuts down the body's ability to degrade neurotransmitters, such as epinephrine, dopamine, some of those other ones. It's not spelled right. Yeah. Too many eyes. Okay, so symptoms include flushed skin, profuse sweating, excess saliva coming out of your mouth, loss of hair, loss of teeth, loss of nails, sensitivity to light. And emotional distress. Which could be anywhere from like crazy or just like memory impairment, depending on the level of exposure that you've had. Does anyone know where we get most of our mercury poisoning in the US from? Fish. Eating fish. Eating raw fish especially. So you gotta be careful with your raw fish, where you're getting it from. Sushi. Yeah, you gotta be careful with that. So, go to a reputable place that serves fairly good food. I think it is, yeah, it's a substantial amount.
Okay.
I mean, but it does build up in your body. So that's kind of a trade-off. Like either you eat a lot all at once, like you drink a whole thermometer, or you have been eating the same, right, raw fish every day for years and years and years.
Is Valhalla reputable?
I would think so. I would think so. Sushi have a food truck, maybe not so much. So
Like the sushi and bee hall?
that should be fine. That should be fine. I would think so. I mean, it's also obviously depending on what. Yeah, I would think that'd be fine. All right, so that's my 2 types of poisoning. Let's talk about the other 2 types of cofactors I have. And then, so going back to number 1, cofactors are needed for redox reactions. Point number 2. Woo! Yeah, I'm not going crazy. Number 1 was metals. Number 2 is that they are either prosthetic groups, like our friend the heme group. That's considered a prosthetic group. It's not part of the protein, so it is a prosthetic group, means an add-on to the actual protein. Either. Cofactors can be either prosthetic groups or something called coenzymes, which you guys are familiar with. You probably just haven't called them that. Coenzymes would be FAD. FAD, NADH, or NADP. Those guys all count as things needed to make the enzyme work, but they're not part of the protein structure. They are associated with that active site somehow.
And you said they're associated with active site needed for the enzyme to work.
Yes. Actually, this should be 2A. Sorry, 2A. Guys, this is more stuff about cofactors and coenzymes. So 2A. Cofactors and coenzymes. Right, just like a regular enzyme, cofactors and coenzymes have to be regenerated to complete catalytic crisis. So just like a regular enzyme, the metal, if it gets oxidized, has to get reduced in order to do the next cycle. Any of these guys, FAD, NADH, NADP, right, they're going to get protonated or deprotonated, which means they have to get the reverse in order to do it again. So they have the same rules as regular enzymes. All right, I guess I'll stop there. We will save the organic drawing for Monday. I know, acid-base catalysis.